Here, we want to understand the capacity of typical frequency flat MIMO channel. First, let us look at the Gaussian channel. So we have source Xi, we generate symbols Xi, which goes through the channel. Then we have the addition of noise Zi, which is normal distributed with mean 0 and variance N naught. So N naught is the noise power. And we receive Yi. We also have a constraint that if a code word Xi is represented as a sequence of symbols, let's say X0, X1 and so on up to Xn, then we have 1 by n summation I goes from 1 to n, xi squared is less than equal to p, which is the power constraint. And among many constraints, this is the easily understood constraint as there is limited power at the transmitter. And one of the most common power constraint is the average power constraint, which we have defined here. And now we want to find out capacity of this Gaussian channel. We know capacity is the maximization of mutual information over all possible distributions of source. So we can write capacity as we maximize the mutual information over all possible distributions of X subject to power constraint. And now from our videos on information theory, we know I of X comma Y can be represented in terms of differential entropy. That means we can write it as H of Y, differential entropy of Y, minus differential entropy of Y given X. And now we can also write it in this form, H of Y minus H of X plus Z given X. So if you carefully look at this term, this is basically comprised of H of X given X, which is equal to 0. And then we have H of Z given X, which is equal to H of Z, because noise Z is independent of the source. So then we can write this expression as H of Y minus H of Z. So now this capacity is the maximization of differential entropy in Y minus differential entropy in Z for over all possible distributions of X subject to power constraint. And we know for a real normal distribution, the differential entropy is given as H of Z is equal to 1 by 2 log 2 by E n naught. So this is the differential entropy in noise. Now this expression we have, but we want to compute H of Y minus H of Z. So H of Y we do not have, we want to compute this. This we have. So we will find out E of Y square, what is the power in Y, which can be written as expectation of X plus Z square, which is again equal to expectation of X square plus expectation of Z square plus expectation of X and expectation of Z. Now this is equal to 0 because we have a 0 mean symbol. This is equal to 0 because the mean of the noise is 0. And what is the power across X square? Let us say it is equal to P, and the noise power is given as N naught. So we can write E of Y square is equal to P plus N. So which is the variance of Y. Then we can write H of Y is less than equal to 1 by 2 log 2 by E, and here we substitute the variance of Y, which is equal to P plus N. So then Mutual information I of x comma y can be represented as the subtraction of h of y minus h of z. So we can write it as 1 by 2 log 2 2 by e p plus n minus 1 by 2 log 2 2 by e n, which is equal to 1 by 2 log 2 p plus n divided by n, or we can write it as 1 by 2 log 2 1 plus p by n. And this is the well-known expression of the capacity of Gaussian channel. So we have log 2 1 plus signal power by noise power. Now if we look at the complex Gaussian, yi is equal to xi plus zi, still the expressions will remain the same. So again we can write it as I of x comma y is h of y minus h of y given x. So this can be written as h of z, and here we have h of y minus h of z. So now in case of complex Gaussian, so we have the differential entropy is given by log 2 pi e raised to power n determinant of k. So instead of the previous expression, now we will substitute this expression as the differential entropy. So we get log 2 pi e, again p plus n, minus log 2 pi e n. So this is again equal to log 2 p plus n divided by n, which is equal to log 2. This is okay. So we get 1 plus p divided by n, and which is the well-known expression for complex Gaussian channel. So this is the expression for complex Gaussian channel. So this expression easily leads us to the capacity of SISO channels. So now we have seen the results for SISO channel. Let us move towards the MIMO channel. Now we want to find out capacity of flat deterministic MIMO channel. What is capacity? We know it. What is frequency flat? What are the conditions for frequency flat? That also we know. What is MIMO channel? That also we have studied. So new term here is deterministic. Deterministic means for a particular realization of the channel. That means for a particular realization the channel is known to us. Okay, so assumption is that we have empty number of transmitters, empty number of antennas at the transmitter side. We have MR number of antennas at the receiver side, and the channel matrix H is defined as HMR cross MT. So now the received signal at the receiver can be written as y is equal to square root of Es by MT Hs plus n, where n has the dimension MR cross 1. So this can be easily, all these dimensions can be easily written by looking at this particular diagram. We have empty number of transmitter antennas, we have MR number of receiving antennas. So noise is at the receiver, so we have MR number of antennas, so we get MR cross 1. Then S, how many symbols that we are transmitting, since we have empty number of transmitter antennas, so we are transmitting empty symbols and takes the dimension MT cross 1. Then we know H has a dimension MR cross MT, and the received signal Y is again MR cross 1. So here Es by MT, signal power is divided equally among the empty number of antennas. So next thing we will define RSS, covariance of source. RSS is defined as expectation of S into S Hermitian, and expectation of S is equal to 0. So then we also have the power constraint, that the trace of RSS is equal to MT, because we want the total average power constraint to ES. So that's why we need to include the power constraint here. So assumption here is that H is known to the receiver, implies it is estimated at the receiver, and there is perfect estimation or perfect CSI. So there are no errors. It is an ideal estimation. So then we can write capacity as maximization over f of s, I of s comma y. And from the previous slides, we have seen that I of s comma y can be represented as h of y minus h of y given s, and this can be further reduced to h of n because h is that deterministic and noise is independent of symbol s. So now we have this particular expression. So we have h of n and h of y. So h of n is not in our hands. We cannot maximize this h of n or not work on h of n. But on h of y, we can work on it and we can maximize this h of y. But first we need to compute what is h of y. Now again, we want to find out h of y. We know from our previous expression h of y depends on covariance matrix of y, that means RYY. So we need to compute first what is RYY. So RYY can be written as expectation of y Hermitian. So we can first write the expression for y and then we multiply it with y Hermitian. And if you have Hermitian here, this can be written as root Es by mt S Hermitian H Hermitian plus N Hermitian. So basically you want to multiply this with this. So when you multiply, what you will get? So let me write it here. So you will get expectation of Es by mt H S S Hermitian H Hermitian. This is the first term. Then second term is root Es by mt H S N Hermitian. Then you get Es by mt N S Hermitian H Hermitian plus N Hermitian. So basically what we have done, we have basically multiplied this term with this term and this term, and then with n with this term and this term. Simple multiplication. So what you will get? You will get E is equal to Es by mt H, since we have SS Hermitian. So we'll get expectation of SS Hermitian. So we have written down here expectation of SS Hermitian. Then we have expectation of N Hermitian, which is written down here. So both this term, second term and third term will be equal to 0 because here we will have expectation of S which is equal to 0, and here also we have expectation of S which is equal to 0, and apart from this we also have expectation of noise which is also equal to 0 and expectation of noise which is also equal to 0. So these two terms will become 0 and we will get the first term and the last term. So now what is expectation of SS Hermitian? This is basically equal to RSS, and expectation of N Hermitian is equal to N naught I M R. So why this is so? Because if you have, let's say this is expectation, and first you define the noise vector, this is N1 to NR, and you multiply it with the complex conjugate of this vector which is N Hermitian, you get N1 conjugate, N2 conjugate, and so on. So when you multiply it, you will get a matrix. In the matrix, in the diagonal elements, you will get expectation of N1 square, expectation of N2 square, and so on. Expectation of N M R square. Whereas in the non-diagonal elements, you will get expectation of Ni Nj conjugate, and similarly here you will get expectation of Nj Ni conjugate. So all these non-diagonal elements would be equal to 0 because noise are independent samples, they are independent. So all these non-diagonal elements would be equal to 0. And the diagonal elements noise for n1 and noise for n2 both are same, which is equal to n naught. So we take n naught outside and this will become identity matrix. So that's why we have written n naught multiplied with I m r. So now we have the expression for r y y. We simply substitute this expression into this particular expression h of y. So we get h of y and we already have h of n. The noise covariance of noise is given by n naught I m r. So then you simply do the calculations and you will get the typical capacity of the MIMO channel, which is given as capacity is maximize. We have the power constraint. So we are maximizing it over RSS, and this is the expression for mutual information. So we have log 2 determinant of IMR plus ES by MT N naught H RSS H Hermitian. So how you are getting this? You are basically getting this by substituting the RYY expression and then you divide it with this one. You will get IMR plus ES by N naught because it is ES by N naught is here. ES by N naught, ES by MT N naught H RSS H Hermitian divided by N naught. So this is how you will get the capacity expression. So at this point, this is the capacity of MIMO channel. Next, we will try to find out what is the meaning of this particular expression.